Hello everybody. So in this video we're going to continue with chapter 2, functions, specifically 2.2, relations and functions. So to the left we have an example of a function. In this case it is a set of inputs that we can call the domain. That's the name for the input values, domain. In this case the domain is a list of different animals. And the set of outputs, which is known as a range, is in this case the life expectancy of said animals. So if you take the elephant has a life expectancy of 50 years. A goat has a life expectancy of 10 years. A horse also has a life expectancy of 50 years. A rabbit has a life expectancy of 10 years, just like the goat. And finally, we have the tiger, which has a life expectancy of 25 years. Now, this is a good example, a real life example of a function. So this is a function. Now, why is this a function? All functions are relations, but not all relations are functions. So this one is a function because every input in the domain or every animal has only one possible output in the range. So for instance, the elephant can only have a life expectancy of 50 years because it wouldn't make any sense for the expectancy to be less than that or more than that. It's a number for all elephants, the life expectancy. And same with each one of these animals. Each one has one possible life expectancy. And it is not a problem if, for example, the life expectancy of 50 years is the same for the horse and the elephant. So you can repeat the set or the numbers or the values that are in the output set. That's not a problem. What cannot happen is if you have the case, like we have here to the right, where we see something called merely a relation. So in this case, X maps into Y. But notice that, for example, the number 2 maps to two different values in Y, as you can see there. So this is only a relation. 5 also maps into two different values. It maps into 0 and it maps into 4. Therefore, this is only a relation and it cannot be a function. So what cannot happen is to have repeated solutions, so to speak, or repeated outputs for each input. So what does that mean graphically? Well, graphically speaking, a function would only have one output or one y for each x value. So let's suppose on this graph that we have here to the left, let's suppose that we have 1, 2, and 3. Notice that if you draw vertical lines, the x value 3 maps to only one point on the graph for y. 2 also maps only on one point, as we can see here. And 1 also maps to only one point on the graph. That means that each x value maps to one unique y value, because if this is 4 in y, both 1 and 3 map to 4, but that's not a problem. Remember that the y values can repeat, but what is important is that the x values map only to one unique value. So 1 only maps uniquely to 4, and 3 also maps uniquely to 4 as well. What cannot happen is what we see here, where this is not a function, like this circle. So notice that this x value, let's suppose this is 2. The 2 would map into two different y values. It would map here and here. So this is just a relation, not a function. Same with this other value. Let's suppose it's 1. It maps to two different y values. Therefore, it's not a function, just like this other case that is not a function. Notice that this unique x value, let's say 2, maps to 3 different y values, or 4 different y values actually. So you can see that. Therefore, this is not a function. And this is something called the vertical line test. So basically, if you draw a vertical line through a graph and it goes through the graph more than once, then you can say it is not a function. So next, we're going to talk about the concept of domain and also the concept of range. So domain, we can describe it as the set of inputs. And range is the set of outputs. So in notation for mathematics, X describes the domain. So for this graph that we see here, f of x, this graph, you can see that the domain is this set of values that start at this point and end at this point for this particular graph. So let's suppose that this is 1 and this is 5. So the way you would describe the domain, you would say, well, the domain is x values such that 1, right, x is greater than or equal to 1, but less than or equal to 5. So in this case, this would be the domain, and the domain describes the x values that are inputted into the function. Now you cannot make a list with this case like 1, 2, 3, 4, 5 because a line has an infinite amount of points. Therefore, you have to consider all real values between 1 and 5, including 1 and 5. Now the range would be for the y values. So let's suppose that this minimum here is 3 for y and the maximum is 6. I'm just supposing that so we can illustrate the example. So the range for y, we would say, well, y is greater than or equal to 3, but less than or equal to 6. So again, the domain is the input values or the set of inputs, and it's in terms of x. And the range is the set of outputs or y values, as we can see here. Now, if you look at this graph that we have here to the right, let's suppose that they ask us to find the domain and range of this function here. So they tell us that the function is y is equal to x squared plus 1. So remember that the domain is the set of x values. Now, this function is actually infinite, although it should have arrows here indicating that it continues infinitely up for both sides of this graph. So what would be the domain? To estimate the domain here, you need to look at the function itself. So y equals x squared. And the domain is all the set values or all the values of x that you are allowed to plug in here. So is there any limitation for squaring a number? Or is it possible to square any number? Well, the fact is that you can square anything, right? Therefore, x is such that x belongs to the real numbers. So this would be the domain, any real number. How about the range? Well, this function has a minimum value, as you can see, because it's a parabola that goes upwards. So the minimum value, as you can see here for y, is 1. So that means that 1 is a minimum. Is there a maximum? Well, no, because as we said, it goes up infinitely. So y is greater than or equal to 1. You can also write this backwards, right? You can say, well, y is greater than or equal to 1. This would be the range, all the possible y values that can come out of this function. Okay, so here we are with example 2.10. And part A says, estimate the volume of a cube as a function of the length e of each edge. So recall that the volume of a cube is simply going to be this value times this value times this value. In other words, the area of the base times the height, right? So that means that we can express the volume as being equal to e times e times e, which is e cubed. So the volume as a function of the length e of each edge is v equals e cubed. So notice that this here is what's called the independent. This is the independent variable. And v is dependent on e in this case, right? The volume depends on the edge of the cube. So that means that this here is the dependent variable. So how about B? Well, B says express the total surface area S of the cube as a function of the length e of each edge. So s is the dependent variable, and it is equal to something e, right? So how do we calculate the surface area of a cube? Well, a cube has 6 sides that are squares, right? So that means that the surface area can be expressed as 6 times e squared, because e squared would be the surface area of each square. So in example 2.11, they ask us to find the domain of each function. So remember that domain is the input values, right? The set of input values. Okay, so for letter A, what we have here is not exactly a function, a formula, but rather a list of coordinates. So notice that the first coordinate is -6, -3. Then we have -1, 0. Then we have 2, 3, 3, 0, 5, 4. So that means that these are points on a Cartesian plane. So -6, -3, let's suppose it's around here somewhere. That would be that point. -1, 0, let's suppose it would be around there. 2, 3, let's suppose it would be up here. 3, 0 would be down here. 5, 4 would be somewhere around there. So it's just a set of points. And the input values here, remember that this is the Cartesian plane. This here is the x-axis, and this here is the y-axis. So the input is going to be the x coordinates. And we just make a list. So in this case, the domain, we make the list, would be all the x coordinates for these points, right? So -6, -1, 2, 3, and 5. If they had asked us for the range, then it would be the y values, right? Okay, so for B, it says volume of a sphere. So V is equal to 4/3 pi r cubed. So the domain is the input values, right? So here the domain is the independent variable that we can use, right? The independent variable is r. So the question here is, what values can I put into r? What values can I put into r? Well, I cannot put in any negative values because there's no such thing as a negative radius in the case of a sphere. So r must be greater than 0, right? Now, we don't really want to use an upper limit on this because there's spheres that are gigantic, right? Like planets and stars and things like that. So we can say that the domain would be any r value greater than 0, because if you have a radius of 0, then you don't have a sphere, right? So it has to be greater than 0. For C, so C is really an example of a function, right? Y is equal to 5 over 2x minus 6. So again, domain, the input, so x. So what are we allowed to put into here? Is there any value that we cannot put into x here? In the case of x squared that we did before, we said we can use any value for x. So we said x belongs to the real numbers. So let's start with that. We can say, well, x belongs to the real numbers. And that would be half right, because there is at least one value. In this case, there's exactly one value that is not allowed in the domain. And which one is it? Well, remember that when you divide, you cannot divide by 0. If you divide 5 by 0, this has no solution. If you plug that into the calculator, it's going to give you a big error, mathematical error. You cannot divide by 0. And since you cannot divide by 0, it means, therefore, that 2x minus 6 cannot equal 0. That cannot equal 0, or what happens is that it becomes undefined. So, what do we do here? And if you do the math, you're going to get that x is equal to 3. So if 3 is a value of x that makes the denominator equal to 0, that means that x cannot equal 3. So this here would be the domain. All real values except 3. D. So in D, we have another function that says y is equal to the square root of 3 minus x. So again, is there any limitation with square roots? Well, yes, there is. There is a limitation with square roots, and that is you cannot have a square root of a negative number. It has no real solution. So what that means is that 3 minus x must be greater than or equal to 0, right? That's what that means. 3 minus x must be 0 or more. It cannot be negative. So if we solve for x here, we can just move this x to the right because it's negative, and I don't like using negative signs. So let's say 3 greater than or equal to x. So that means that x has to be less than or equal to 3. And that makes sense because if you plug in 3 here, notice that if you plug in 3, this is equal to 0. But if you plug in anything greater than 3, then it's going to be negative. So that means, again, that the domain for D, let's write it properly, the domain would be x values less than or equal to 3. In example 2.12, they want us to find both the domain and range for this function. So let's start with the domain. Remember that the domain is input, or x, and the range is output, or y. So when we do this algebraically, we have to analyze the function. So y is equal to 1 plus the square root of x minus 2. So are there any limitations here for the input values? Well, yes, right? Because this is a square root. So like the previous case, x minus 2 needs to be greater than or equal to 0. Now, if we solve for x here, it's simply going to be that x is greater than or equal to 2. So this is the domain. Okay, so the x values start at 2. So that means that you get 2, 2 comma 1, 2.1, 2.3, 2.2, 2.5, etc., right? Or 3, 4, etc. So 5. So it means that x keeps increasing, increasing, increasing. The lowest value is 2. So what happens when we plug in 2 here? 2 minus 2 is 0, so we get 0. That means that the first y is going to be 1. What happens if I plug in 3? If I plug in 3 here, I'm going to get 3 minus 2 is 1. Square root of 1 is 1. 1 plus 1 is 2. So that means that 1 is the lowest value because anything else you plug in for x is just going to make y larger and larger and larger. So that means that the range is y greater than or equal to 1. I'm going to graph this, and I'm going to show you what this means graphically. Okay, so here we have the graphing calculator. And remember how to graph, right? First you click on the y equals button, which is on the top left. And this is where we graph. Now I had some previous graphs in here, which I'm going to clear out. I'm just going to hit the clear button and clear that out. There. And then I'm going to plug in the function that we want to see graphically. So we said it was 1 plus square root, second function square root, variable x minus 2. Minus 2. So there we go, and then you hit the graph button. So this is again 1 plus the square root of x minus 2. And let's not forget y equals, right? The right notation. So the domain we said is the x values or the input values. So notice that here, right here, you can see that this is 2. And notice that the graph for x values starts at 2 and goes into infinity. Just like we said that the domain is x values greater than or equal to 2. How about for y? So if you look at the y-axis, this is the value for 1, and it starts at 1 and it just goes up. Although you see it rising slightly, believe me, this goes on into infinity. So that's why the range is y values greater than or equal to 1. So next we have example 2.13, and it says find the domain and range of the function h of x is equal to 1 over x minus 2. So because this is a fraction, remember that the limitation for fractions is that the denominator cannot equal 0, right? So the only value that will make this equal to 0 is x equals 2. Therefore, we can say, well, x can be any real number, but x cannot equal 2. Otherwise, it will make the denominator 0. So this would be the domain. How about the range? Well, Since we cannot plug in 2, that means that this cannot equal 0. So what's a characteristic of these type of functions? If you have a constant on top of something with a variable, like here, right? Like this part where it says x minus 2. But if the numerator is a constant, there's no way in the world that this will equal to 0. This cannot equal to 0. There's no way you can get 0 out of here. The only way you could get 0 is if you had something with x on top in the numerator. So that means that the range is any real value for y, but y will never equal 0. So we're going to see this graphically as well. So we said that h of x is equal to 1 over x minus 2. So this is what we have to plug into the graphing calculator. So we would say 1, so we go here to the calculator, 1 divided by, and notice that it gives you a slash, x minus 2. Now here you have to be careful because 1 is being divided by all of x minus 2. If you type in, let's say, if you type in like this, x minus 2, the calculator is very stupid, and it's thinking, if you do that, that you're asking it to graph 1 over x minus 2. And that is obviously not the same as this. So we need to use parentheses, okay? So keep that in mind, please. All right, so how do we do that then? Well, let me get rid of this here real quick. What we do is that right after that slash, right, the divide symbol gave us that slash, we would go parenthesis, and then we write x minus 2, and we close parenthesis. Okay, so let's hit the graph button and see what comes up. So there you are. Okay, so remember that we said that the domain was x belongs to all reals, but x cannot equal 2, because that's where the function becomes undefined, right? We were doing h of x is equal to 1 over x minus 2. And here, if we plug in 2, it becomes undefined. So that's why we have this weird shape. Notice that this is x equals 2 right here. And if you draw a vertical line, right, an imaginary vertical line here, you can see that the graph does not come close, or it comes close, but it doesn't touch the value of 2. So this is what is called a vertical. This value 2, x equals 2, is what's called a vertical asymptote. That's a vertical asymptote. For the range, we said that y can be any real value, but then I explained that y can never equal 0. And you can see that here. Notice that the graph comes very close to 0, but doesn't really touch it, and then drops here when it gets to, well, 0 for y, right? And then when it gets to the value of x equals 2, it just drops down into negative infinity, and then pops up back here, but then just comes back down and stays above 0, never quite reaching it. So that means that this is a horizontal asymptote. So this is what's called, y equals 0 is what's called a horizontal asymptote. Right? And we said here that x equals 2 is what's called a vertical asymptote. Okay, so now we are on the final example for this video, which is 2.14, and it says find the domain and range of the function f of x equals 1 over square root of 9 minus x squared. So this will be the most complicated case that we're going to analyze and that you are going to be required to solve. For this, we're going to use the graphing display calculator. Okay, so we're going to graph 1 over, or divided by, right, the square root of 9 minus x squared. There we go. So now just hit the graph button, and there's the graph. Okay, so here, let's recall a couple things. Now, the first thing I want to tell you is the graphing calculator here is wrong. Why? Because it's not showing the whole graph. The reason is that because as you approach, so remember that the function is 1 over the square root of 9 minus x squared. So what happens when we divide 1 by values that are very close to 0? Values that are very, very close to 0. So if you grab 1, and let's say you divide it by 0.00001, that's very close to 0, but not 0. If you divide 1 by that, you can test it out in the calculator. You're going to get a number like, in this case, 1, 2, 3, 4, 5. So 1 and 1, 2, 3, 4, 5. So 100,000. So that means that as you get closer to -3 and to 3, you're going to get very large values. So what happens is that there's a gap here because the calculator is incapable of showing that this line goes up very quickly. So this would go up here as well very quickly. And these would be asymptotes. -3 would be an asymptote, and +3 would also be an asymptote. Why? Well, what happens if you plug in 3 here, or -3? So positive or -3. That's going to give you 9, and 9 minus 9 is 0. Okay, but from the graph, we can tell very easily that the domain is x values that are greater than -3, but less than 3. Notice that in this case, I'm not saying equal as well, because as we saw here, 3 or -3 would make it undefined because it would make this 0, and we cannot divide by 0. So the domain is x between -3 and 3, as we can see here in the graph, not including those values. How about the range? Now, you might be tempted to say, well, from 0 to infinity, but if you notice, there's a little gap between the graph and the x-axis, so we need to find that minimum. So the graphing calculators have a function that can find that minimum for you. So if you look at the top button right next to the graph that says trace, that one can help. On top of that, it says calc. So we got to go second function and calc. And notice that here we have several options, and number 3 says minimum. So we're going to click on number 3, and it's going to ask for a left bound. So we move a little bit to the left where we think the minimum is, and we hit enter. Then it's going to ask for a right bound, move a little bit to the right of where we think the minimum is. We hit enter, and then it has a guess with a question mark. That means yes, right? So hit enter again, and there it is. The minimum is right here where y is equal to 0.33333. Now notice that this is just 1/3, right? 1/3, 0.333. So that means that the range is y values greater than or equal to 1/3. And that's easy to see. Why? Well, because if you plug in 0 here, if you plug in 0, what do you get? You're going to get 1 over square root of 9, which is equal to 1/3. So that's the minimum value of this function.